Okay, so I want to continue the second part of our short course, and our second speaker is also an expert in the subject of frequency combs, and in particular their applications. This is Nate Newbury, who runs is the group leader of the Fiber Sources and Applications Group at NIST in Boulder, Colorado. And he and his group members have been looking at highly coherent fiber laser frequency combs to transfer, or for frequency transfer, metrology, precision spectroscopy, and a lot of other applications that I've actually followed over the last several years as I've gotten to know Nate's work. Before joining NIST, Nate was actually came from MIT Lincoln Laboratories, and he is, in addition to being a fellow of NIST, he's also a fellow of the Optical Society of America, and we're very pleased that Nate could join us today and give you his insights and also an overview of all of these remarkable applications. And so Nate, I'll head over to you.
Thank you, Kerry, and it's exciting to be here and be at the point where combs at least can be considered for space missions, and I want to thank Kerry and Nan and Stephanie and Scott for organizing this and getting us all here. My talk's really going to follow on Scott's and try to look at some applications of combs. I'm going to give, as I'll say, just as a disclaimer, kind of a NIST-centric thing, and of course talk about applications that we've been looking at collectively at NIST because we know about those and I have the view graphs on them, but there are a lot of other applications people have done. But maybe this at least provides some kind of a snapshot of the types of things you can do with frequency combs. So there are a lot of different, Scott showed a different picture. There are a lot of pictures of illustrating the number and the diversity of applications you can have with frequency combs. Here's one such picture. So all of these are based on the comb, and there are a range of applications. Obviously, comb started, as Scott mentioned, and was really driven, one of the motivations by Jan Hall and colleagues here was to be able to measure optical clocks. So combs provide a way to give you this coherent link from optical to RF. And so in so much as they're doing that, they're also intimately related with frequency and time transfer. I'll talk a little bit about low phase noise microwave generation, and Scott mentioned that, and astronomical spectrograph calibration. Of course, the broadband nature of the comb and its coherence lends it to precision spectroscopy. And then by a similar token, its timing stability and its broad bandwidth helps with coherent LADAR for ranging or other measurements, vibrometry. And you can shape it maybe for waveforms, and maybe it has some applications as a tool in communications. In all of these, really what you're doing is you're taking the comb in a laser-based metrology or sensing system, and you're using it. And you can think of any of these in the frequency or the time domain, those sort of two faces that Scott mentioned. And in the frequency domain, ultimately, often the comb is acting as a spectral ruler, right? And it's totally obvious for that in terms of the astrograph calibration, for example, spectrograph calibration. Or if you think of it in time, it's acting as a ruler in time because the pulses of the comb are coming out at very specific times with a very well-defined rate. And so depending on the application, it's easier to think of it in one way or the other. One of the things I think this really oversimplifies is the situation, and I show all these applications using this frequency comb, but in fact they use very different types of frequency combs. They have very different requirements on the comb that are satisfied by very different systems. So for example, a clock, you might want a comb that has residual stabilities pushing 10 to the minus 19 or 20 in terms of its fractional stability, but you don't need, and you need light where the optical clocks are, but that's it, right? So you need a very well phase-locked stable system at some particular comb teeth. Whereas for something like, say, molecular spectroscopy, you really want a broad spectrum of the comb that's fairly flat and ideally covers the wavelength region you're interested in, but its stability doesn't have to be great. Part 10 to the 8 is still already way more than you need. And if you get out here in some sort of waveforms, maybe you don't need much stability at all, but you want your teeth to be spaced fairly far apart to be commensurate with the sort of modern high-speed electronics. So while we say all of these use a comb, they're very different combs. And I think as we go forward and think of space missions, each of these combs has, they can be hard or easy combs to build, okay? So with that introduction, I thought I'd just sort of go through some overview of some different comb applications that may have some relevance here for space missions and ones that we've sort of been involved in. All of these are terrestrial, and most of them are laboratory-based, although we are sending some light out over the air. In fact, most comb work has been in the lab. Of course, the exception for combs in the lab or on the ground is the recent work by Menlo and Ronald Halsworth this year on putting a comb up on the sounding rocket, and the Koreans have had a femtosecond fiber laser in orbit. Again, as I mentioned, I'm giving a very NIST-centric view, so I apologize for that up front, but at least it gives you a snapshot of some of the applications. Then I'll just have one slide mentioning a few other applications I think we'll hear about later this week. It's probably not totally inclusive of all of them, but at least mention a few. So these are the applications I wanted to talk about, ranging from sort of precision microwave generation, and Scott sort of hinted at that some already, to calibration of astronomical spectrographs. I'll talk some about ranging, because it's a very basic measurement and may have some relevance to space missions. And then about molecular spectroscopy, particularly for the measurement of greenhouse gases. And finally, some work we've been doing more recently on looking at how to do a timing synchronized network, where you're trying to really push the synchronization of timing across a network from picoseconds to femtoseconds. There isn't anything really holding all these together other than the fact they use a comb, and obviously I decided precision because I put that in all the names. Some level, and I mean that more in the general sense, right? Combs have some precision or accuracy we're applying. So I was trying to figure out how to go through this, and basically I'm just going to go and sort of the number of combs, so it's sort of like a Dr. Seuss one comb, two comb approach. So these are first systems that use one comb, and then I'll talk about these two systems that use two combs, and this system actually uses three combs. So at some level it's a measure of complexity, but not completely, because often in these systems, and I'll try to mention this each time, the comb does its job, right? But it's part of a larger system. And often the limits are not due to the comb's giving you the frequency accuracy you need, or the collimated beam, but it can only do so much, and the rest of the system, the limitations might come from the rest of the system, or the complexity. So with that, I'll talk some about microwave generation. This is really sort of a bread and butter thing of the combs. This is the same slide that Scott showed, except my gears don't move like his. So the idea here is you have a stabilized CW laser, right, that's turning at a rapid rate, the period of the optical waves, and using the comb as a divider to divide that down to a lower rate, maybe the rep rate of the comb or a harmonic at the microwaves. And the advantage of the comb, as Scott said, is it's phase coherent. None of these cogs ever slip, so you have a phase coherent transition here. And that's really, at some level, a basic feature or property of what the comb can do for you. So the idea is you want to use this for microwave generation, and the reason is very simple. You can make something up here that's very stable now. And then if you can phase coherently transfer it down here, this is equally stable. So this is what the basic idea. You start with this ultra-stable CW laser oscillator. So the whole system is relying on the fact, well, you have a CW laser stabilized to a cavity, and the whole system is relying on the stability of this cavity, okay? And they've always been, as Scott mentioned, they've been very stable for years, and they're getting even more stable. There's a huge amount of effort going in developing better and better optical cavities. And then what you do is you lock a comb to that using the self-reference locking that Scott mentioned. And now you have a system where the spacing between these comb teeth is exactly this optical frequency divided by some integer, which is a large number. And when you hit this on a photodiode, now switching to the time domain, you have a pulse of optical pulses. You get a train of RF pulses coming out, and you can take RF harmonics of these to generate your microwaves, okay? And the beauty of this is that if this is all from here on down is done perfectly, you basically take any of the timing noise on this cavity, which is related to any essentially length jitter between these mirrors, and you translate that to the timing jitter on the RF output without any excess noise. And in terms of phase noise, which is often the way these things are described, what you've done is you've taken the optical phase noise and you divided it by n squared, where n is the division number here. So in practice, this is an older slide, just to give you an idea, and people are working on shrinking all this. But conventionally, you have an optical cavity that has a pound River Hall lock, and you're stabilizing light to it, and then a comb, and this is Tara Fortier here. This is a Thai sapphire comb, but now you can do it with fiber combs. And then the third and equally critical part is the photodiode that basically takes you from optical to microwave. And there's been a huge amount of work improving these in terms of low timing jitter and high power handling. So that's the system, right? It's just, in principle, it's simple to draw. You have the cavity, the comb, and the photodetection, and you get this division. And in practice, you really can realize this. So if you think of it in terms of timing noise, which is preserved as you go through frequencies here, this optical frequency division, this technique, gives you, say, 2.5 femtoseconds of timing noise integrated over these Fourier frequencies versus 300 femtoseconds from a more conventional sapphire dielectric. And usually phase noise is described in terms of phase noise power spectral density that's shown here. So this is a log scale plot of how much phase noise, how much sort of wiggle of the optical wave you have at 10 gigahertz versus Fourier frequency. And the conventional curves, conventional systems, even high quality ones are up here. And the blue curve is the optical frequency division result. So it does very well at low Fourier frequencies, things close into the carrier. So this is obvious interest for maybe some precision radar or something where you need, or any situation where you need to look at low Doppler shifts, for example. So with that, I'll switch to now a totally different application. I'm going to sort of jump around between these applications. And this is another set of slides from Scott Didham's group and on searching for exoplanets. And this is a nice example of the comb being used literally as a spectral ruler. So these are slides from Scott and his graduate student Gabe Ukas did these. And the idea here is you want to look for an exoplanet. And so basically you're looking at the light from this star, and because it moves a little bit, the spectrum shifts, right? Just from Doppler shifts. And you want to detect that shift, which is tiny. This is being done in a number of places. Again, Menlo has a very large effort to do this at ESO. To look at Doppler shifts from Earth-like planets orbiting sun-like stars, where you're looking for these tiny Doppler shifts. And you're going to use the comb to measure those. And hopefully Ronald will talk some about that later in the meeting. There's another system you can look at, and this is what Scott and Gabe were looking at, which is basically looking at potentially habitable planets orbiting M-dwarf stars. The Doppler shifts here are a little bit bigger, but also they're in the near infrared, in the H band of the atmosphere, which is interesting because that's well matched with fiber frequency combs. So this is what the experiment looks like, right? You collect the light, and it comes down to this very high quality spectrograph, and you measure the spectrum of the star, and then in parallel you have a comb, which might be referenced to a absolute time standard, and it produces comb teeth, hopefully widely separated, and you measure them at the same time. So you literally have a spectral ruler underneath your spectrum, and you can look for small shifts with time. And fiber combs are portable, right? They could box it up and drive it and then set it up on this Pathfinder spectrograph. This is what the experiments look like, right? You have a telescope that collects light, it comes into the spectrograph, and then you have to pipe in comb light coming from, in this case, a fiber comb, where they've filtered the teeth to have them at 25 gigahertz and sent it in parallel with the light from this fiber. And of course, the hard part is getting all this stuff so everything's co-aligned, essentially. And here's an example of a spectrum. You have your spectral ruler and the star spectrum, or here's your spectral ruler and the spectrum, and you can look for small shifts, which they've done looking at this Eta Cassiopeia. And if you have questions, you can ask Scott. But the uncertainty bars here are, say, about 5 meters per second, and they're already sort of state of the art, and the goal is to push them further. But this is a nice example. The comb can support much better than this, right? The challenge here now becomes the rest of the system is the limiting factor, which is a theme that often comes up. So with that, I'll talk a little bit, some detail about precision ranging. Here's a slide on why we might be interested in that for here, and the obvious reason is some sort of future formation flying between smaller satellites to develop a larger synthetic aperture. For that, it's obvious you're going to need to know some distance between the satellites. That's relatively easy. I think the hard part here is you need the precision attitude control. Because if you have a large synthetic aperture, whether you're looking down or up, you need each guy to be pointing, or each subsystem to be pointing with a pointing attitude control, which is equivalent to the diffraction limit of the synthetic aperture, right? So it's a very difficult attitude control measurement. And this hasn't been done, but just to throw this out here, the way you might do that kind of thing, right, is have a ranging system with a couple of different, say, retros on your subsystem here, and you measure them, and you can get some idea of relative distances, and hopefully help some out with the attitude control that way. So this is the main interest for just ranging alone. Obviously, ranging comes in with a sort of GRACE mission, but there they can do it with microwave or future laser-based interferometric measurements. Maybe the comb has a role there, particularly if you have to have a system where you're not always within one wavelength and you need some absolute distance measurements in some more complicated constellation configuration. It's not my sort of speculative there. And obviously ranging has obvious applications if you're trying to assemble or put together large-scale optical systems. So the combs aren't playing a role here, but it's worth thinking about, can they provide some help? Can they do something more or make life easier? And the possible advantages is, right, you do get, as I'll show, you can get absolute distance with interferometric precision and fast update rates using a comb, sort of within one optical source. The length is always calibrated back to an RF standard rather than some other physical etalon. So it's traceable to some time standard. And because the comb has high bandwidth, you have some immunity from spurious reflections or cyclic errors that can come up. So to think about laser ranging a little bit, here's a grossly oversimplified view of it. And you can think about two different types of laser radar, right? You can imagine if you send a pulse of light out and it comes back, basically you just measure the time of flight of the pulse going out and back. And if you only have one pulse in the ring here, you get absolute distance. But your resolution is limited by how well you can find the center of this pulse. And the other extreme is laser interferometry, where you send a CW light out and have it come back, and you basically build an interferometer and measure the phase shifts on the light that returns. In that case, you have sub-wavelength resolution, but you have no absolute range because you don't know what fringe you're on. So the way around that is you just add more wavelengths, and then you can sort things out and basically remove that wavelength ambiguity. So just looking at this, it's obvious the comb can combine these, right? We have a source that is pulses of light in the time domain. In the frequency domain, we have a whole comb of frequencies, so we have a massively multi-wavelength source. So again, going back to Scott's sort of two faces of the comb, you can think in either way, a comb is attractive for ranging. In the time domain, we have these pulses that are very stable with respect to whatever the comb's locked to, with femtosecond level stability, and we have a stable carrier frequency as well if we've done a full offset CO stabilization of the comb. So we can do interferometric measurements with the carrier. And in the frequency domain, you have all these wavelengths of light, right? So you can do multi-wavelength interferometry with as many wavelengths as you want. So these are equivalent pictures. It just depends whether you want to think about it in time or frequency. And I would say it's been evident from the beginning that combs are great for ranging. And there have been a lot of people and this is just a partial list of different ways people have used combs for ranging. Okay, there's just a slew of different ways people have implemented them. I'm going to talk about two ways. This is some stuff we did a while back. This was sort of what we call dual comb ranging. So it uses two frequency combs. And the idea is shown here. We have a signal comb, which has a repetition rate. I'll call it f-rep. So that's how fast the pulses are coming out. And we'll think about it in the time domain. And we'll send the pulses out. And in any ranging, we need a reference plane. So we'll look at a reflection from some well-defined plane and then a target. And we're trying to measure this distance by measuring the time of flight between these 2 points. So this pulse train goes out and the pulses come back, and we have a reflection from this surface, which is, I guess, this one, this red pulse here, and a reflection from the target surface, which is here. So we have these two reflections here and here, and we want to measure how far apart they are. If we just hit them on a photodiode, it doesn't work too well because we lose all the fringes and you have all the timing jitter associated with the photodiode detection, which you can get rid of in optical frequency division, but it's not trivial and you need a lot of light power. So we didn't want to do direct detection. So instead we do heterodyne detection, but we have a comb here, so we're going to do heterodyne detection against another comb, a local oscillator comb. And we're going to phase lock it together so it has the same, say, carrier frequency, but it runs at a different repetition rate, runs it a little faster. So now you have two pulse trains hitting this photodiode, and they walk across each other, right? You can think of this pulse as sort of stroboscopically sampling whether or not the red comb pulse is there. And you get interferograms. The other way to think about it is you basically built a linear optical sampling scope. So now when you look at the output of the photodiode, you get these fringes when the blue and red pulses overlap, and then when they overlap again. And this is literally a readout of the reflections of the red comb pulses here. And this time axis here in the lab might be stretched, but because we know the exact phase locking between these combs, we know what it is an effective time, the same way you would with just a sampling scope in the RF domain. So this is nice because it's heterodyne detection, so when the pulses overlap, we have shot noise limited detection. There is as I'll talk about, a penalty because of the stroboscopic sampling, but nothing beyond that. It's fast, we can do the measurements in a few hundred microseconds, and it has all the accuracy of the combs. So these combs are locked to some RF reference or an optical reference. All of that timing accuracy is carried through here. There's no degradation other than from shot noise. So to make the measurement, right, what we're doing now is we have two measurements we can make. The arrival of these pulses gives us the time of flight. So if we look at when these envelopes arrive, we get a time, and we multiply that by the group velocity over 2, and we have the range. But in addition, there's a phase on each of these, which represents the relative phase between the carrier here and the carrier here. And assuming this one is stable, we can measure then the phase of the light that came back from the reference and the phase from the target, and do the same interferometric measurement you would have done with a CW source with the same ambiguity. It's actually lambda over 2. But you can look at this and say, well, this is all measured with the same light signal on the same path and the same photodetector. It's just the different ways of looking at the phase of the measurement. And so if we can get this time of flight measurement down to sub-wavelength, below lambda over 2, we can identify this integer number and drop all the way down to interferometric ranging. And so that's what's done here. So this is the range uncertainty versus time. So this is from hundreds of microseconds out to hundreds of milliseconds. And this is done in the lab over 1.5 meters, but we added fiber to at least mimic long range without the photon loss. And basically, you're at a few microns right away, and that time of flight averages down, and at some point, we're well below half a wavelength, and we can drop down to the interferometric measurement and hand over to it and be less than 5 nanometers at 60 milliseconds with absolute ranging information. And you can get, not only that, you can actually get these ranges to agree if you take into account the GUI phase shift and other effects that will shift the interferometric measurement from the time of flight. So that works great. The problem, you might cringe a little bit, is these are fully phase locked combs, right? We have optical coherence between them, so it's not a simple comb. You can back off and say, maybe I don't need the interferometric precision, right? Maybe I can get down to 100 nanometers or somewhere down here, and that's good enough. And in that case, you have a much simpler system. You can actually just use some femtosecond fiber lasers or any sort of femtosecond pulse source, tune them up so they have, approximately some difference of rep rate, but then just count the rep rates and process the signals. And there's no phase locking here. It's all just counting and processing. And that's true in a lot of comb systems. You can really, sometimes you don't need to really phase lock the system. You can just measure some signals and process the heck out of it and get what you need. And in this case, the sacrifice is the phase here between these two signals has no particular meaning because the phase of these carriers is not defined. But the time of flight is perfectly valid still. And so we did that measurement. That's what's shown here. So in black is the previous data, and in blue is now with these free-running systems and just counting the rep rate. And you can see it actually even does a little better, and that's because we ran here with twice the repetition rate of the combs. And many of these systems, and this one included, things get better with higher rep rate combs, provided you have enough photons. The disadvantage of, so this is nice, it's rapid, it's do high precision. We have, I should mention this. If you look here, if there was a spurious reflection, and there will be in real systems here, anywhere in here outside of this 300 micron window, we can identify it and exclude it. And that really helps with systematics. The problem, of course, is you need two combs, and if you're willing to give up the interferometric measurement, it's not such a big deal. But the big problem is this linear sampling. It is heterodyne detection, but every time there's no pulse there, we sort of have information in that there's no pulse there, but it's not an efficient use of photons. And if you compare it to a swept laser, sort of multi-wavelength interferometer done by sweeping a laser frequency across, there's a penalty in terms of how many photons you're using. And so we wanted to look, so you need nanowatts for this system. We wanted to look here where you could maybe get away with femtowatts and see, can we get both advantages? And so basically then you're, and this is true for spectroscopy too, you're at the point where you say, well, why can I just use a swept laser the way I would normally, but calibrate it against a comb and keep the accuracy and keep the high speed? And the reason, again, to do this is the swept laser ranging or swept laser spectroscopy. Basically, anytime you have a laser that can exist and sweeps over the wavelength you want to access, you're going to do better SNR-wise with that. So the conventional way to calibrate a swept laser, right, is you have a gas cell for absolute calibration and maybe an etalon to give yourself some markers. With the comb, you just sweep the laser against a comb, and their markers are now the teeth of the comb. And again, here's a situation where if you don't care about the absolute optical frequency, just its bandwidth, you don't need this to be absolutely stabilized. It can just be a free-running laser, and you count the rep rate. So you might say, well, okay, this is simpler than this, right? And there is greater complexity here. You need a comb. But there are a couple of advantages. Again, the absolute calibration now of the laser sweep frequency, and therefore the range, is not reliant on the physical size of this etalon, but you can just count the rep rate here. And so you're traceable straight back to an RF standard. You do phase continuous measurements. I think the big thing is, this is kind of clunky now if you do it with a fiber system. The big thing is this type of architecture is compatible with some of the chip scale systems Scott was talking about, whereas it would be very hard to cram this onto a chip. So I think it's probably more, from a practical point of view, it's really waiting for the chip systems to develop. But in the meantime, we have done measurements with this. This is an example of a ranging measurement where we have a swept laser and a comb to calibrate it, and it's basically a FMCW or swept source OCT or whatever. It has different names. Basically sweep the frequency of the laser and come back and do a heterodyne measurement. At the same time, you're measuring the actual instantaneous frequency of the laser and processing, again, putting in an FPGA and doing a lot of processing. And you can get the range out. This is with just femtowatts or tens of femtowatts of light coming back. So now we can look off diffuse scattering surfaces where the return is less. And this is a motorcycle piston where we took an image of it. The accuracy here is traceable to 100 nanometers or so, limited by some systematics. Actually, depending on how well you know the air, might be worse. The noise is limited by speckle. So it's, again, a situation where the comb's giving you everything you could have, but your actual noise, it will be limited by something else fundamental, in this case, speckle noise. I'll show you another image. We took a picture of a shoe, not just because we hadn't have one around, but we were thinking about forensics and impression casting. So we made, just give feeling for this here it is. The type of data you can get with this. So that's the optical table the shoe was on, and there's the shoe. And this was at 10 meters distance, okay? And we're just looking at diffuse scattering off the sole, and you can see the treads of the shoe and the wear marks. And it doesn't take that long to get this image. Now you can get 3D images like this with other systems. The difference here is we're actually doing this at some range at 10 meters, and even though you can't see it here, we do have absolute calibration of the range. In fact, the calibration in this case, like many things, is limited. The distance we get accurately from the comb, the calibration is limited by the XY coordinate and mapping from R theta phi to XY. We took pictures of other things. Here's a dead moth we found in the lab, and there's a cactus from somebody's office. This is the most precise image of a cactus ever. I think it's dead now. Now I was going to talk about molecular spectroscopy. So the combs are really well suited for spectroscopy of atoms and molecules. Our goal here is to think about using them for greenhouse gases. The motivation here is obvious, right? You want to accurately measure CO2, methane, water, and all the other atmospheric chemicals that might contribute, to identify sources and sinks, to check inventory models, to make sure people don't have leaks in fracking fields and so on. And this is a huge area, and again, to oversimplify it a little bit, the way it's done now is you can have point sensor, which is a cavity ring down spectrometer, which you can drive around, you can fly around, do whatever to take maps of the area. Or, of course, you can go the other end and have a satellite-based system, and this is, it measures column density of CO2. This is some old data from GOSAT, and now we have OCO2, and I think there's a meeting this week, a science team meeting on OCO2 here on campus. We were looking at saying, well, can we do something in between, get some sort of kilometer scale on the ground in the boundary layer to provide maybe some truth data for this system and to check the spectral models, right? Because what you're actually measuring in any of these systems is gas absorption. You want to go to gas concentration, that needs a spectral model to link absorption to concentration. And so we're looking at ways to do that over 10 kilometers, 1 to 10 kilometers, and try to develop a continuous monitoring system. To do that, we're going to use the comb to do absorption spectroscopy, just standard linear absorption spectroscopy. And the comb's a great thing for that, right? You have this collimated single mode light and go a long way. Depending on your comb, you can have coverage in the visible IR or UV, and you have these nice narrow delta teeth, delta function sort of teeth. So you don't, if you do it right, you're not going to have any instrument line shape to distort the spectrum. And because for greenhouse gas monitoring, what you're interested in is a precision measurement at, say, 0.1%, it's very important to not have any distortions. And of course, you have the built-in frequency calibration. But you have to do the detection, right? And the way I drew it here, it doesn't work. All your comb teeth hit the photodiode. One other thing. So the other nice thing, if you just start out at least looking at the main candidates of CO2 and methane, is they have these nice bands in this 1.6 micron region where there's an atmospheric transparency and where fiber lasers work. This is a signal we're looking for. And then spectral models, you connect this absorption to a concentration. So how do you do the detection? I mean, you have the obvious choices. You can use a grating spectrometer or Fourier transform spectrometer. The problem with those, unless you have a really long one here, is they don't have the resolution to pull out individual teeth. Another approach which is really intriguing is this VIPA spectrograph, which is similar to the astronomical spectrograph, where you just really high resolution spatial dispersion, and you can get resolved teeth if the teeth are far enough apart. The way I'll talk about is this dual comb spectroscopy, which really lets you fully resolve the teeth, even if they're kind of close together. And it's had a lot of traction, as I'll mention, in the community lately, as a way to exploit the comb for spectroscopy. So dual comb spectroscopy, this is, I guess, came up in Scott's meeting, Scott's talk. So this is a situation, again, where we're using two combs. We're going to phase lock them together and beat them against each other. And we're going to phase lock them such that at one tooth they overlap. These are their optical teeth. And then this guy has a different rep rate, so its comb teeth walk off the other one. So now if you think of this as an array of CW lasers, basically each pair of these CW lasers, when they beat together, you're going to get an RF frequency that's the difference in their optical frequencies. Okay? And since each pair have a different difference, you get a different RF tone. And if you've limited your bandwidth appropriately, there's a one-to-one mapping. So you know that this RF tone had to come from that pair of optical teeth. And what you've done is you've mapped from the optical to the RF. And so, of course, if you put a gas sample in here, you get absorption on this comb, you see it in the RF spectrum. Okay? And that's really all there is to the dual comb detection. It turns out you can realize it in the lab. This is some earlier data we took. So the first data we took to really show you could see this in its full form. So we had two fiber combs. We put a gas in that absorbed at 1550, and we had a 3 nanometer filter here. And we hit it on a photodiode. And we expected then to see the filter shape, right, mimicked in our RF spectrum with some dips from the gas absorption here. And what we saw was this. So here's this filter shape. This is 3 nanometers of bandwidth. And maybe there's a few dips, but you're not seeing the resolved teeth. And the reason is that we're just not looking hard enough. This isn't to scale, and there are tens of thousands of comb teeth in here. So if I blow it up, this is just the same data zoomed in. First of all, here's a nice dip from HCN. And if you keep blowing it up, you see it really is individual RF comb teeth. And they're, in fact, if you keep blowing it up, they're about a hertz wide, related to the optical line width, how well we did the phase locking here, so the line width of these. So you really do get this picture, if I go back to just one dip, of these comb teeth coming down and up. And again, now you have this one-to-one mapping, so you can take this dip and you can map it to the optical. And in addition, you get the phase measurement too, which is interesting. So you can really realize this picture exactly depending on how hard you work on the phase locks here. And there's been a lot of work looking at dual comb spectroscopy. So this is a similar picture to what Scott showed. This is sort of where frequency combs have been demonstrated, at least at the time we did this view graph. And down here is where people have demonstrated some form of dual comb spectroscopy. In some cases, they're just a proof of principle demonstration with a free-running comb. In some cases, like the one I just showed, they're really doing it with a fully coherent, stabilized system. But they're all showing the basic idea works fine in different spectral regions. And I want to emphasize, I didn't emphasize it before, that basically this is the same thing as terahertz time domain spectroscopy. I think we'll talk about that later in the week. It's exactly the same thing. We just moved it up to the optical, and it happens to have a different name. And these are all terahertz time domain spectroscopy measurements. That's basically the same technique. So to do the greenhouse gas detection, we're conveniently located in here where we can take advantage of these erbium fiber combs. So we wanted to do that, so instead of looking at a gas cell, we take the dual comb spectrometer and we send it out over Boulder out to a mirror that's up on a mesa about 1 kilometer away and comes back. And again, the goal is just do linear absorption spectroscopy, measure the absorption over this path, and then fit it to extract CO2, methane, actually HDO, H2O, and equally important, the air temperature from the shape of the CO2 spectrum. Because the air temperature, if you want a fraction of a percent measurement, you have to know the air temperature or the mixing ratio. This is what the dual comb spectrometer looked like in this system. This was, at this point, a lab-based system. We're since trying to build one up that's more portable. You have 2 femtosecond fiber lasers that you amplify, and then you broaden in highly nonlinear fiber that Scott mentioned. And then you have a whole bunch of light coming out. Most of it is useless because it doesn't overlap the methane and CO2 bands. So we shape it in just a spectral shaper and then send it out. And in this case, we sent both combs overlapped out so that you can then do a multi-mode detection because the modal distortions are common mode. But you can also send just a single comb out. And then we detect it back here, right? And this is the type of thing you see. So this is in frequency. If you're a chemist, they should put in wave number. And this is intensity that's detected. So this is covering from 1600 to 1670 nanometers. And this overall shape is the spectral shape of the comb. We purposely didn't let light out here because there's no interesting gas absorption. But this overall shape is just the shape of the comb. And that's what I meant earlier. If you're doing spectroscopy, having a nice smooth spectrum of the comb helps a lot. And it took a while even to get it this smooth. It's an area that needs a lot more engineering. The signal, the gas absorption we're looking at, and there's 700 different absorption features here, are these little fuzzes. This isn't noise, so that's a dip, that's a dip. Even in here, the little dips, this is the CO2 band. Here's another P and R bands of the CO2. And you can't really appreciate this, but there are really 100,000 comb teeth in here. So there's a whole bunch of spectral data points. And it covers about 8 terahertz. So basically, we take this and we fit out the overall shape of the spectrum, and then you just fit these little dips to get the gas concentration. And that's what's shown here, and I'm just showing the main gases we looked at. This is running over 3 days. These systems can run a long time. This is CO2, methane, and H2O. And CO2, of course, we're at 400 parts per million now, right? We used to be at 300, and we're going up. Methane is close to 2 parts per million, and water varies all over. Even in Boulder, we have some humidity. And if you blow this up, you can see variations. So our data is the colored data. The black trace is the point sensor that was sucking in air near the path. And you can see the CO2, you see lots of variations as clouds of CO2 pass by, and same with methane. And obviously, this is just showing a proof of principle experiment. If you could take this data in different paths, feed them into some larger model, you could start to try to develop a picture of where the CO2 or methane is coming from and going to. But you can see we have pretty good agreement here between the point sensor and ours, particularly given they're sampling different volumes. But there's corrections that are applied. There's a big correction to get this overall shift between this black curve and the red curve. And that's seen in other areas too in CO2 monitoring, and again, has to do with how good is your spectral database that connects absorption to concentration. So one of the applications here is to just try to take some data and get that agreement much better. I should mention, so will this work in space? Well, probably not, right? This is 8 terahertz of bandwidth, 10 to the 5 comb teeth. In order to have a measurable signal, you got to have some photons back in each tooth, and that's an awful lot of ways to slice up your light, right? You can only produce so much power, and you start dividing it up to that many spectral bins. It's not going to work that well over super long distances. But you can go back up and say, well, you don't necessarily need that much, and there's some interesting data taken by our colleagues at NIST Gaithersburg using just EOM combs. As Scott had mentioned, you can make a comb by just taking a laser and modulating it. You're not going to get the same bandwidth you get necessarily unless you go to the efforts that Scott mentioned. But even at a narrower band, you can still do a dual comb measurement. And here's some dual comb measurements they took of CO2 in a resonant cell, and they added some CO and it has water. And the nice thing about this is at least you have enough bandwidth that you're covering 1 or 2 spectral lines at once. So again, you have a lot of points across the absorption line for low systematics, and the measurements are taken kind of simultaneously at all data points. So that's at least something to think about. Then I guess I was going to now totally switch areas and talk about precision timing across a network for synchronization. Scenario we've been sort of actively looking at for a little while now. The motivation for this is really, a lot of it was originally optical clocks. So this is, Scott showed a slide on this. This is just a slide on optical clocks. And as Scott mentioned, what they really are is it's a laser that's stabilized to a cavity. This is a spherical cavity that Till Rosenman had developed with a very fast loop. So you end up with very narrow, stable laser light. But the frequency of that light is limited, is set by the cavity. And so to guide it, then you're going to have a slower loop where you lock onto some atomic transition, either with laser-cooled, say, strontium atoms or aluminum ions or whatever your atom or ion of choice is. These are very complicated systems, but they can work really well, right? And you can get 10 to the 17 or now even 10 to the 18 digits of accuracy, which is incredibly precise. And here's sort of how small it is, but one of the things is that 10 to the minus 17, that's the type of frequency shift you get just from the gravitational redshift on Earth in our 1G gravity, if you raise something 10 centimeters. And that was done and shown in a nice experiment by Till Rosenman and Dave Weiland and Dave Hume and James Chow, where they took 2 aluminum ion clocks in the same lab and they raised one versus the other, and they saw the frequency shift they'd expect, which is a heck of a way to measure 15 centimeters in the lab, but it's really intriguing, right, if you think about moving these far apart from each other. So where does the comb come in? Well, the output of the clock, right, is this 1 micron laser that's ticking at 3 femtoseconds, and unless you have another one just like it, it's hard to do the comparison. And the comb's role really is just to translate that signal faithfully to some other wavelength or some microwaves or wherever you need it. And one way to think about it is to translate it just to the separation of the pulse train coming out of the comb. So if this was ticking at 3 femtoseconds, if I lock a 200 megahertz frequency comb to it, now I have something ticking at 5 nanoseconds with femtosecond level stability. So now we have a signal we can do something and do measurements, some sort of precision measurements, right? This is the most precise thing we have around. But most of those measurements are going to require sending these signals somewhere outside the lab. And if you try to do that in the RF domain, if you try to go all the way to the RF and start sending the signals around, you're going to have a problem, because RF links typically are not going to be able to support the type of timing stability that the optical clocks have. So this is fractional uncertainty versus averaging time, and clocks are even lower now, or way down here, the best ones. And RF links have more residual noise than that, just because it's running at a lower frequency. So the same thing that drove you from RF to optical clocks drives you from RF to optical links. And so that's what we're interested in optical links, and the sort of standard summary of reasons is here. One is obviously if we have these great clocks and we want to disseminate their time, we're going to eventually need optical links between them. Not in the near future, but in the way future, maybe some ground to satellite to ground optical link to connect them. Because otherwise it's very hard to figure out how to get it around the Earth. Because for fiber you need very specialty fiber, and it'd probably be prohibitively expensive, even as expensive as this is. You can imagine a more sort of smaller scale, but still a network, again, related to formation flying, that's either looking down or up, where you're going to really send timing signals around to all the different components. So they're acting as a synthetic or coherent system for navigation or sensing. And then there's the gravity effects that I mentioned, this idea that these clocks are 10 to the minus 18, so they're sensitive to a centimeter change in gravity height. So there's interest in experiments in relativity. Or you flip it on its head and you say, well, I'll measure it, use it, the clocks to measure the gravity field on Earth. You're never going to get the types of maps, of course, you can get out of something like GRACE, but maybe it can provide some calibration markers. And given the alternative, which is some guys that really literally walk 2 kilometers a day and map out do a line integral of gravity across the Earth, the clocks are intriguing for that. I think there's different, depending on who you talk to, there's different views on the clock-based geodesy and whether it's how useful it will be or not, depending on who you're talking to. But it's intriguing to think about. So in all of these, like in particularly this one, what we're really talking about is a network, a timing network, right? So you can imagine you have one of these really fancy, maybe large optical atomic clocks. You're not going to have dozens of them. Maybe you have one, and you're going to want to disseminate its time around. So you might want to disseminate it to, say, one based on this optical frequency division microwave, or one based on a quartz oscillator, or another optical clock. And maybe one of these just has an optical cavity and doesn't include ions. So in these cases, the goal, just to really simplify and look at just one link here, our goal is to have our 2 clocks and our observer, and he wants to see that these are ticking not only at the same rate, but at the same time. So that's what we're trying to do, is say, okay, these clocks are both going around accurately with femtosecond level timing precision, so that if I measure the time, and this is from some actual data, I measure the time at the master site and say it's exactly 845 hours, 59 minutes, and 29 seconds, the slave site's going to agree to that down at this digit. So that was our goal in this sort of free space link, and it's hard to do, and the reason is that you're trying to send light over the air, okay, in our case, or in this maybe ground to space. But you're trying to send these light signals across and you have turbulence, so it really destroys your beam. And if this will, so instead of having the nice Gaussian beam that you'd have, I've totally lost my cursor. There it is. It gets all broken up. This is just a simulation, but this is what it looks like. So you sometimes have signals, sometimes you don't. In addition to that amplitude noise, what really kills us here, right, is you have phase noise. There's piston noise, essentially apparent distance changes between the 2 sites because of variations of the index of refraction along this path. And of course, the 2 sites can move. Even on the fixed buildings, we have the buildings sway. And if you have any motion between them that's bigger than 3 nanometers per second and you aren't controlling it, you've lost your part 10 to the 17 accuracy. So even if these are 1, 10, or 100 kilometers apart, you need to control their relative motion to 3 nanometers per second. So that looks really hard, but what saves you is the same thing that saves you in the RF domain. The atmosphere is reciprocal. So if you have a single mode link, and only a single mode link, and by which I mean you have single mode fiber here that you send the light out, this is kind of by nature multi-mode, and you collect in a single mode fiber here, then anything that happens to the light going this direction happens to the light going this direction, in the limit of no polarization effects and forgetting about time-dependent effects. It's not true if you have a multi-mode fiber. So that means any of the amplitude noise on this light happens this way, and any of the phase or timing noise going through this way happens in reverse. And that 2-way reciprocality saves us. It lets us cancel out this noise the same way it does in the RF microwave domain. So what we do is a 2-way time transfer, and I'll just show you the basic idea, right? And this has been around for a long time. You have 2 sites, site A and site B, each with their own independent clock. And you say, okay, at time 0, site A is going to send a pulse this way, and at time 0, its time 0, site B is going to send one this way. So the pulses go across, and you measure. This guy says, okay, my pulse got here at the nominal 0, what this guy thinks is 0, plus the time it took to go across the link, plus any time offset between my clocks, because I might not agree that his 0 was really 0. And this one does the same thing. You have 0 plus the time across the link, and now it's minus the time difference of the clocks, because now I'm measuring this time with respect to this time. So it's pretty obvious then if you take these 2 measurements and you take their sum, you have the time across the link, which is the range between the 2, okay, if you knew the speed of light. If you take the difference, you're sensitive to the time offset between the clocks. And independent of the link. So that's all we want to do. So for synchronization, right, we take that measurement, and we basically transmit it over a communication link. We do a real-time calculation, and we feed back, and we speed up or slow down the slave clock to make sure it agrees, its time agrees. And this is what we've implemented. It's just complicated because we implement a pseudo-random binary sequence phase-modulated light, sort of a more conventional approach to do course time synchronization between them. And then we actually start sending comb pulses with femtosecond timing back and forth to do a finer timing. And then, of course, we need a communication link, which is done optically on the same hardware as this. And so the whole system ends up looking kind of complicated, and this is a boiled-down version. But there's this PRBS, or pseudo-random binary modulated light, to do the course timing that's going back and forth. And then we have comb pulses that are going back and forth. And so at each side, our slave clock is this comb locked to an optical cavity, and the master is another comb locked to an optical cavity. But we can't just send the comb pulses over and do direct detection for the same reason as in the ranging case. The photo detection, we'd lose our femtosecond timing. So instead, we have a transfer comb, and we set the slave and transfer to run at different rep rates and do the same sort of heterodyne linear optical sampling here and in reverse here to measure the ever-progressing time offset between the slave and transfer combs, do the same measurement between the transfer and master, and ultimately link it all together so we have the timing between the master and the slave. And so when it's all done, we should have the same clock output at each site. They should have the same time. And we need to check that. So first we need to define the clock output. And in this optical system, our output is the pulse train from the comb. And we've labeled each pulse to say what time it is. So this pulse, say, we'll call 8 a.m. All right, when it arrives somewhere at a reference plane that we've had to calibrate out. And the master site, we're going to say, okay, when this pulse arrives at a reference plane, and let's make it a common reference plane, it's also 8 a.m. So to check whether all this information worked and whether these two sites are working right, we have a shorted link. This will do a folded geometry where we'll check that these two 8 a.m. pulses arrive at the reference plane at the same time. And if they do, then we've succeeded. So basically what we do is we put the two ends near each other and send the light out off a mirror and come back, all right, to try to tell how we're doing. So here's the system. Basically, this is the NIST campus. This is the same 1 kilometer link I showed. We bounce back and forth 4 times for 4 kilometers. Here's the two comb. Here's a master, slave, and transfer comb. Again, they're next to each other, but they're only linked with this one truth data fiber to check their timing. Otherwise, they're separate systems. And then up here is our mirror, where we bounce the light off of it. And I think, yeah. So here's a picture of it. We had to close it up because the homeless guys were moving in. This is our sign asking them not to. One guy offered to paint it if we let him live there. So this is what, you can see turbulence. This is the Ahini off a corner cube to give you a feeling. So this is really what you're fighting. And this is over 1 kilometer. The turbulence is much worse over longer. So how do we do? So again, we have this link. We're going to short them and compare their time here. This is the time offset we see, and it wanders from plus or minus 20 femtoseconds. So it's 1,000 times better than anything you could do in the RF. And most of this wander is due to the fact that the lab isn't temperature controlled. And to do the comparison, we have a meter of fiber that's subject to some temperature variations and its length changes. So it causes this effective wander. And to get this 20 femtoseconds right, we have to speed up and slow down the clock. This is the rate of the clock and the correction that we apply. So, I mean, at some level, this is it. This is plus or minus 20 femtoseconds. You can see the fuzz, but you can analyze it in the standard way you do for clocks and look at the timing deviation. Again, this is the timing deviation now between the real time or the absolute time at each site. It's not linked to any other absolute time scale, but it's not a timing deviation between the relative time change, but an absolute time sync between them. And it's below a femtosecond out to about 6,500 seconds. And it drops down even to a few hundred attoseconds, which would mean that the length, this reciprocality, is valid to 70 nanometers over 4 kilometers. So that's the timing deviation. It's a little, I think, it's easy to plot these. I think it's a little easier to picture what's going on if you think what we really have are these two sites. And again, our clock output is these optical pulses. And what we're saying is even though these are connected only by a 4 kilometer link, we're going to make sure their optical pulses arrive at a reference plane at the same time. And so to show that a little more physically, we said, well, let's make the optical pulses interfere spatially by doing a shearing interferometer. And if the pulses arrive at the same time, you get optical fringes. If they don't arrive at the same time, you don't get fringes because the pulses aren't interfering with each other. And so I think, heard that played. So that's what's shown here. This is a focal plane, and we have PPS, or pulse per second bursts of pulses to mimic a microwave system. And with the system synchronized, and this is what the system thinks the timing is, you get really good optical interference because these 100 femtosecond pulses are literally interfering with each other because they're arriving at the same time from these otherwise two separate systems. And in about 30 seconds here, we can just push a button, right? It's all automated, it's FPGA controlled. Push a button and tell them to don't sync up. And then the slave system will wander off because its cavity doesn't agree with the cavity of the master site. And you start to lose the fringes because now the pulses are coming one after each other, another. And then in about 48 seconds or so here, we hit the synchronized button again, and you get fringes again. And basically, if there's a turbulent dropout, right, you would have this. This might happen anyway, depending on how long you didn't have light. But as soon as you have light again, you can sync up. And not only can you sync up, you know how far off you were, so you can make corrections. So that was done over this round trip 1 kilometer. We bounced back and forth 4 kilometers. We have gone further just recently. This is out, once we got permission, out over Boulder. There's Valmont Butte, which is sort of near the dump, and there's a trail up here, and we walked up and put a mirror up here, and a camouflage mirror that points back at NIST. And if you look, so now we're coming out of the top of NIST, and we send light out. Again, these terminals, here the two terminals are actually further apart. Experiment. And it goes out to Valmont Butte in the distance and comes back. And we can, I think this is just some initial data. So this is looking through a big telescope at the mirror, and you can see turbulence causing things to move around. That's wind in the trees. And we're synced up. This is actually between an optical and microwave source, so it's synced up most of the time. Well, not even most of the time, but about 30% of the time there's enough photons coming back and forth. And that's basically all this amounts to going long distances. Can you get enough photons back? This isn't anywhere, of course, in terms of space distances, this is short. This is, as I mentioned, you get the range, so this is 11.7 kilometers. But that's an awful lot of turbulence to go through, right? It's a lot more turbulence than you'd go through if you went up, because you're going horizontal for that distance. And we had very little power. So with that, I'll probably sort of wrap it up. The data, the first 2 sets of slides I showed were from Scott's group, and Frank and Tara on the microwaves, and Gabe with the Astrograph telescope. All the later stuff was all from people from our group over the years. In particular, a lot of it started out with Ian Coddington and continues with Ian and Bill. The time frequency stuff I just talked about was really driven by Laura Sinclair and Jean-Daniel Duchesnes and Fabrizio Giorgetta and Bill Swan. And the spectroscopy continues, and that the data I showed was really part of what Greg Rieker developed, who's now a professor at CU. And of course, we benefit from continued collaboration with Laval on CO2, with NOAA, with Scott's group, and with the optical clock group. So I didn't cover lots of applications, which hopefully we can talk about this week. Obviously, there's a whole set of fundamental scientific tests that are really interesting. It's interesting to think about the comb for communications, particularly the chip-based ones. I think if you talk about people doing that on the ground, they have systems that work. They don't like the lack of redundancy, right? You might have with a single comb, although you could have as many combs as you want. But there is a lot of advantages because basically you have a single source that produces that much, and if you have a coherent source like that, maybe you relax the requirements on your digital signal processing, and there's a big improvement in power. And of course, I think that we'll talk some more later this week about terahertz spectroscopy. And I think there are other applications. These were just some of the obvious ones I didn't cover. I think initially, one other comment is maybe a while back we'd say, well, if you really want to put a comb and do something with it, you want something that's really revolutionary, otherwise it's not worth the effort of the comb. I don't think that's necessarily true, right? I mean, just for ranging, which is sort of well matched to the comb, combs are getting simpler enough that to see whether it's worth it or not, I think you have to look at the whole system. Because while combs are complicated, you get a lot out of the one box. And so if you already have to have 3 or 4 lasers, maybe the comb isn't that much of a bigger step. And then the final thing, I think, and maybe Carl will talk about this, is the thing that's really different is can you really use your photons efficiently? And if you're within the satellite, maybe that matters. But particularly as you go to longer distances, that's a challenge for some of the comb-based systems we talked, configurations we talked about. And as Scott mentioned, I mean, it's, I think, depending on the application, unclear what platform you might want. So with that, I guess I'll wrap it up. I mean, frequency combs are a new tool. I sort of mentioned some applications. There's many others. And hopefully this week we'll try to pick some that would be well matched as sort of first steps for space missions. Thank you.